Dear learner, I welcome you all to this online teaching session. Today we will discuss about HPLC method development, a practical approach. Before learning about HPLC and its practical approach, let us know what is chromatography. Chromatography is known as color writing. The word chromatography is obtained from Greek words chroma means color and graphein means to write. For any chromatography, you require stationary phase, mobile phase, and sample. Stationary phase is a fixed phase, it is not moving. Solid and liquid can be a stationary phase, but gas cannot be a stationary phase. Mobile phase, it is a moving phase. Liquid and gas can be used as a mobile phase, but solid cannot be used as a mobile phase. If you want to use solid as a mobile phase, you have to dissolve it into an appropriate solvent. Sample to be analyzed by chromatography can be in the form of solid, liquid, or gas. Now, what is the principle behind any chromatography? All chromatography is based on an equilibrium of sample between stationary phase and mobile phase. So, this equation shows the equilibrium of your sample between mobile phase and stationary phase. X is a sample. So, distribution cost constant Km can be written as Xs upon Xm, where S stands for stationary phase, M stands for mobile phase, X is a sample. So Xs is a amount of sample in stationary phase and Xm is the amount of sample in mobile phase. So if you have high Km value, that means this value is high. That means sample is more retained by the stationary phase, or you can say the amount of sample in stationary phase is high. To describe any chromatographic process, let us consider chromatographic process with six theoretical plate. Theoretical plate is nothing but imaginary concept where it is believed that sample is equally distributed, or sample is not equally distributed. The sample is in equilibrium between the stationary phase and mobile phase. So let us consider that we are placing 80 microgram of sample, and we also have to consider that the sample which we are loading having distribution constant 1. We are assuming that the distribution constant of the sample is 1. So when the sample, that is 80 microgram of sample is loaded on the stationary phase, so what happens when it comes in contact with the mobile phase? As the distribution constant is 1, so sample will be equally distributed between stationary phase and mobile phase. So here the 80 microgram will be equally distributed. So here the amount of stationary phase is 40 in stationary phase, amount of sample is 40, and in here also in mobile phase the amount of sample is 40, that is in mobile phase. Now the mobile phase is moving. So the mobile phase will carry this 40 microgram to next theoretical plate. Again there will be a equal distribution of your sample, and this process will go on till the sixth theoretical plate. So this will be the scenario at sixth theoretical plate, and if you combine the total amount of sample that is present in stationary phase as the mobile phase, this is the total amount of sample present, and if this total amount is plotted versus number of theoretical plate, you will get ideal Gaussian peak shape. And here there is a maximum amount of sample that is eluted. This value is here. So this point is known as retention time in HPLC, where maximum amount of sample is eluted from the chromatographic system. Now what is HPLC? HPLC is also known as high pressure liquid chromatography. It is also known as high performance liquid chromatography. It is known as high pressure liquid chromatography because the pressure involved is very high, because the particle size is less than 50 micrometer. So stationary phase will form very compact mass, so mobile phase will not be able to pass through that stationary phase without any pressure. So some pressure is required to pass the mobile phase through the stationary phase, which has formed very compact mass. The HPLC is also known as high performance liquid chromatography because it offers sensitivity, speed, and reproducibility. This is the instrumentation of HPLC system. You require a solvent reservoir to contain mobile phase. Then pump will be there for flow of mobile phase from one end to another, or flow of mobile phase through this column. Then injection system for sample that is also known as sample introduction system. Column is the heart of any chromatography where actual separation takes place, and of course detector for detection of any signal. This is the image of Dynix HPLC 3000 series. Let us see some important terminology. What do you mean by normal phase chromatography? In normal phase chromatography, the stationary phase will be relatively polar and mobile phase will be relatively non-polar. Reverse phase chromatography, the stationary phase will be relatively non-polar and mobile phase is polar. And retention time, as I have discussed, it is time elapses from start of chromatogram to the elution maximum of the sample. So when you start the chromatogram, the time elapses from start of chromatogram to the maximum elution of sample. It is known as retention time. Here you can see that at 8 minutes, the maximum amount of sample is eluted. So this is our retention time. What do you mean by number of theoretical plate? It is an imaginary concept where it is believed that the column is divided into various steps, and at each step there is an equilibrium of sample between stationary phase and mobile phase. The number of theoretical plate can be calculated from various formula. N is equal to L by H. L is the length of column and H is height equivalent to theoretical plate. This can also be calculated by formula 16 TR upon W whole square, where TR is retention time of the peak, W is the peak width at the base. N is also calculated by the formula 5.54 into TR upon W half whole square. Again the TR is retention time of the sample and W 1 half is peak width at the half of the peak height. So we can see from this diagram, this is the width of the peak at base and this is the width of the peak at half of the peak height. So if we consider this is 100 centimeter, so we have to consider peak width at half height. So half height will be 50 centimeter, and this at 50 centimeter you have to consider the value, and that can be taken as a W half. Resolution, it is a baseline separation. So resolution is nothing but how the peaks are separated, how the critical pair or adjacent peaks are separated from each other. You can see here that here the resolution is 1 and here the resolution is little improved, that is 1.5. So the peaks are very well resolved here as compared to this condition. Resolution can be calculated by the formula Rs is equal to Tr2 minus Tr1 upon W1 plus W2, where Tr2 is a retention time of second peak, Tr1 is a retention time of first peak, W1 is a peak width of first peak and W2 is peak width of second peak. Now capacity factor, it is a measure of retention of the peak. This we can very well understand using this diagram. For calculation of capacity factor, the equation is K dash is equal to Tr minus T0 upon T0, where Tr is retention time of that particular peak and T0 is a dead time of column. In our subsequent slide, we will learn in detail about how to calculate T0, that is dead time. So for calculation of capacity factor of any peak, you require retention time and dead time of the column. Another important terminology is selectivity factor, that is alpha. Alpha is given by ratio of partition coefficient or capacity factor of strongly retained peak to that of the less strongly retained peak. So alpha can be calculated by two formula. One, you can take a ratio of partition coefficient of two peaks, and another is you can take a ratio of capacity factor of two peaks. But you have to keep in mind that the value for strongly retained peak should be on upside, or you can say on, it should be on numerator, and the other value should be in the denominator. Hence, strongly retained compound will have high capacity factor than that of the less strongly retained compound. Now coming to what is isocratic elution. In isocratic elution, mobile phase composition remains constant throughout the run. It will not change. And what is gradient elution? The mobile phase composition changes with time during the run. Means in gradient elution there will be a change in polarity of your mobile phase with respect to time. Now, what are the different principles involved in separation? So, depending upon type of HPLC you are using or type of chromatography you are using, the principle of separation can be adsorption, partition, ion exchange, size exclusion, and chiral. Now, factors affecting method development. There are few listed factors affecting HPLC method developments are nature of analyte, stationary phase, mobile phase, flow rate, column oven temperature, detection wavelength, and injection volume. So in method development, depending upon type of analyte or type of sample, the stationary phase is selected, mobile phase composition is selected, flow rate is set, column oven temperature means temperature for separation is set, detection wavelength in case of UV it is set, and amount of sample to be injected is set. One by one we will see nature of analyte. Now nature of analyte, it can be, the analyte can be neutral, acidic or basic. It can be ionic compound. It can be some big molecules like DNA, RNA, carbohydrates, or it can be chiral compounds. So depending upon nature of analyte, you have to select type of chromatography or type of HPLC. In case of neutral, acidic and basic, if the sample is non-polar analyte, then you have to go for non-polar or normal phase chromatography. NPC is normal phase chromatography. If your sample is polar in nature, you have to go for reverse phase chromatography. In the non-polar analyte will be more soluble in non-polar solvent. So normal phase chromatography where the solvent or mobile phase is non-polar, that chromatography you have to select. While polar analyte will be more soluble in polar mobile phase, and polar mobile phase is used in reverse phase chromatography. So in case of polar analyte, reverse phase chromatography will be a method of choice. In case of ionic compound, say a quantification of sodium, potassium, calcium, in where the analyte is ionic in nature, having some charge, in that case ion exchange chromatography is useful. For separation of bigger molecules like RNA, DNA, or some molecules like carbohydrate with high molecular weight, size exclusion chromatography is used. And for separation of chiral compounds, enantiomers, chiral chromatography is used. Now selection of mobile phase. For normal phase chromatography, PEG can be used. So you have to go for a polar stationary phase because it is normal phase chromatography. Cyano columns are used, amino columns, dial columns. While in case of reverse phase chromatography, the stationary phase will be non-polar in nature, relatively non-polar. So C18, C8 column, phenyl columns are used. C18 means octadecylsilyl. octa means 8, deca means 10. So stationary phase with 18 carbon chain is used, while C8 is a uh, it is known as octyl column. So here the functional group will be the carbon chain with 8 carbon chain attached to silica. So that is used. In case of ion exchange chromatography, you can have cation exchanger column and you can have anion exchanger column. Cation exchanger column for exchange of cations, and anion exchange column are for exchange of anions. So SO3 minus H plus group is used, then carboxylic acid group is used. This is strong as compared to this. This is weak cation exchanger and this is strong cationic exchanger. Anionic exchanger, quaternary functional groups are used, and polyamines are also used. Quaternary amine group is a strong anionic exchanger, while polyamine are weak anionic exchanger. Now selection of column length and diameter. Column length can vary for analytical purpose from 30 mm to 300 mm, while internal diameter can range from 1 mm to 4.6 mm. Now how the column length and column diameter affects the separation, that we will see. Longer columns, they offer high resolution or increased resolution. The analysis time, but with longer column, increases. As you can see from this equation, this is length of the column and this is diameter of particle size of stationary phase. So n is proportional to length of column. So as length of column increases, number of theoretical plate increases, and as per this equation, as number of theoretical plate increases, resolution will increase. So hence longer columns provide increased resolution, but at the same time the analysis time will increase because the sample has to pass through that long length. So analysis time will obviously, it will increase it. And with increase in column length, column back pressure will also increases. Shorter column, the advantage with shorter columns are the analysis time is less as compared to longer column. Small diameter columns, they offer high sensitivity because in small diameter column the volume of mobile phase contained will be less as compared to large diameter column. So if same compound is injected into both in small diameter column, as the volume of mobile phase contained is less, it will not be that much diluted as compared to, the sample will not be much diluted as compared to longer columns. Hence you will get sharp peak and the sensitivity will increase. As I told you, less mobile phase per analysis, but because of small diameter the back pressure will be high. Large diameter columns, with large diameter column you can load more amount of sample, which is not possible here because with small diameter column the amount of stationary phase contained in the small diameter column will be relatively less. So you cannot load more sample with small diameter column, but of course with large diameter column you will be able to load more sample, and of course the less there will be a less back pressure because diameter is large. This diagram depicts the effect of column length on resolution. So you can see that with small length of column the resolution is less, while as the column length increases the resolution also increases. Now coming to dead volume and dead time, this is very important parameter with respect to method development. What is, first we will see what is column dead volume and then we will see what is column dead time. So column dead volume is nothing but it is the total volume of liquid phase that is contained in a column. So the total volume of mobile phase contained in the column will be constant for particular length and diameter of the column. So you can calculate column dead volume using the formula V0 is equal to D square into L into pi into pore volume upon 4, where D is internal diameter of column in centimeter, L is the length of column in centimeter, and pore volume, it will be provided on the column. If it is not provided, you can take 0.7 as a standard value and you can calculate the V0 or dead volume. Now what is dead time? Dead time is time required for dead volume to remove out of the column, and the formula is T0 is equal to V0 upon flow rate. So as flow rate increases, the dead time will be decrease. This slide depicts column dimensions, various columns, their dead volume at given flow rate and dead time. Specifically, I have highlighted these two rows with red color, which is this column is most commonly used, that is 250 mm into 4.6 mm internal diameter. So for this column has a column dead time 2.9 minute. At flow rate of 1 ml per minute, the column dead volume will be again 2.9. If I increase the flow rate from 1 to 1.5, the column dead time will decrease. So why this parameter is very important, column dead time is very important. So whenever you develop any method, your retention time of your analyte or sample should be more than dead time of the column. The sample should not elute, or it should not elute out from the column before its dead time. Otherwise what will happen, this, as you know, that capacity factor K dash is given by the equation Tr minus T0 upon T0. So if this value is high, then this, the entire K dash value will be in negative, and that is not acceptable. And the ideal value of capacity factor ranges from 2 to 8. So, and that also depends on type of experiment you are doing, but this value should not be higher than Tr. So always the retention time of your sample or analyte should be greater than T0. So whenever you are going for any method development, you should keep this T0 into consideration. You have to consider it, and you have to accordingly set your mobile phase, you have to set your chromatographic conditions so that the retention time of the peak is not less than T0. Now coming to particle size of stationary phase. Now what is particle size of stationary phase? It is an average diameter of column packing, or it is a average diameter of particles or stationary phase present in the column. It ranges from 2 to 25 micron. For of course analytical purpose, most commonly used particle size is 5 micron. Now smaller particles, they offer larger surface area, and with small particle, as per this equation, number of theoretical plate will increase, hence the column air efficiency will increase. As n increase, the resolution will increase. But as the small particle, they form compact mass in the column, they produce high column back pressure. Large particle will produce less column back pressure. You can see here the effect of particle size on resolution and pressure. You can see that with 1.9 micron particle size, the resolution is 7.54 and pressure is 655 bar. As the particle size is increasing, the pressure is also decreasing, and here you can see that resolution also decreases. So with small particle size, the resolution will be better, but the column back pressure will be high. Now selection of mobile phase. So mobile phase, you have to select depending upon solubility of your sample and type of chromatography you are using. The mobile phase can be neat liquid, or it can be combination of solvents, or you can also use some solid, but you have to dissolve. As for example, buffers are solid, they can be used in the mobile phase, or they can be used as a mobile phase component, but you have to dissolve it into some suitable vehicle. For example, buffer adds soluble in water, so water is used to dissolve the solid compounds. The solvents and solid compounds which are used should be of HPLC grade or gradient grade. If you are going for gradient chromato or gradient elution, you can use gradient grade. For normal phase chromatography, the solvents used are PET ether, petroleum ether, hexane, chloroform, dichloromethane. Ethyl acetate is also used. Isopropyl alcohol is also used in normal phase chromatography. For reverse phase chromatography, you can go for acetonitrile, methanol, water, aqueous acid, for example, acetic acid, trifluoroacetic acid, phosphoric acid. Then you can use aqueous base such as triethylamine. The acid concentration you have to means you have to control depending upon type of your chromatography. You can use 0.1%, 0.5% or 2% depending upon your requirement and depending upon stability of the column at that particular pH. Now buffer concentration, if you are using buffer, the buffer concentration or solid concentration for buffer should range from 10 millimolar to 50 millimolar. Below 10 millimolar, buffer will lose its buffering capacity, so below 10 millimolar it is not used, and above 50 millimolar the viscosity of your buffer will increase, hence back pressure will increase. So you have to keep in mind. Now what is the importance of buffer or pH of mobile phase? When your analyte is non-ionizable, it doesn't require addition of buffer to the mobile phase. But if your sample or analyte is ionizable, it requires addition of buffer to mobile phase. And the pH of mobile phase should be 1 to 2 unit away from the pKa of your analyte. Suppose the pKa of analyte is 6, so you can go for 1 to 2 unit away, means you can keep the mobile phase pH 4 or you can keep mobile phase pH 8 depending upon stability and type of stability of column and type of experiment you are working on. So this diagram depicts that this is the acidic region and this is basic region. So as in acids, or if samples are acidic in nature, in acidic region they will be non-ionized, and in basic region they will be ionized, and base they will remain non-ionized in basic region, and they will be remain ionized in acidic region. So depending upon requirement you have to set pH. But very important point, you cannot set pH of your mobile phase to that of the pK of your sample. If you do so, what will happen, your ionized and unionized form will be generated, and you will get split peak or you will get tailed peak. As you can see that ibuprofen has a pH, ibuprofen has pK 4.4. So if you keep the mobile phase of pH for this experiment exactly at the pK of your ibuprofen, that is 4.4, you will get this tailed peak. But if you keep the mobile phase pH away from pK of ibuprofen, you will get sharp peak, very sharp peak, or peak symmetry will be better. So this you have to keep in mind. This slide depicts different buffers which are used for HPLC, their pKa and their operating range. Now how will you prepare mobile phase? So very important point, whenever you are mixing your solvents for preparation of mobile phase, just mix it, do not make up the volume, because some of the when some solvents are mixed, there may be exothermic or endothermic reaction. So if you make up the volume, the composition will be changed. So for example, methanol water, it produces exothermic reaction. Acetonitrile, when it is mixed with water, it produces endothermic reaction. So you don't have to bother about a final volume of your mobile phase, just you have to mix two proportion of your mobile phase. Say if I want to prepare 60 methanol and 40 ratio of water, so I have to take 60 ml of methanol and 40 ml of water, mix it irrespective of final composition of my final volume of my mobile phase. So I don't have to make up the volume. Always I have to filter the mobile phase. If it is water, or only solvents are there, you have to filter through 0.45 micron nylon filter. But if you are using some buffers, you have to go for 0.2 micron filter. And for buffer, for adjustment of pH, use dilute acid and base for uh, pH adjustment. Do not use concentrated acid or base for pH adjustment, because small variation in the volume of acid and base added will significantly change the pH. Always you have to go for actual pH, not apparent pH of the mobile phase. Actual pH means what? First you have to prepare a buffer, you have to adjust the pH, and then you have to mix the buffer with appropriate other solvent. Don't mix solvents or buffer with organic solvent then adjustment of pH, that is known as apparent pH. So apparent pH is not correct way to adjust. You have to always adjust actual pH. Sometimes weighing of hygroscopic buffer is very difficult, for example ammonium acid, so you have to take care while weighing of this type of solid materials used for mobile phase preparation. And very important, whenever you are using buffer, so prepare a buffer, adjust the pH, filter it, and then check the ratio compatibility of that particular buffer with some organic solvent. So what you have to do, take buffer into test tube, organic solvent in test tube, and mix it whatever desired ratio you want, and you check whether any precipitation is there or not. Otherwise what will happen, if you directly load these two component or a component of mobile phase into the system, and then system will mix, and if they are not compatible, if the buffer is getting precipitate out, then your system will be choked. Very important point, filter the mobile phase and then sonicate. You have to first filter and then sonicate. Don't do sonication first, otherwise what will happen, during filtration again the air bubble will be entrapped and the purpose of sonication will be lost, because we don't want any air bubble in our mobile phase. So mobile phase is sonicated to remove the air bubble. So first filter the mobile phase, then sonicate to remove the air bubble. Flow rate. The flow rate is a volume of mobile phase passed through the column in unit time. It is expressed as in ml per minute. Flow rate affects column efficiency, system pressure, and analysis time. You can see from this diagram that at 1 ml per minute flow rate, the analysis time is more as compared to at 2 ml per minute, the analysis time is almost half of the this time, because higher flow rate will speed up the analysis time, or it will speed up the analysis. So the retention time will be decreased with higher flow rate. You can see with 2 ml per minute retention time is 2.9 minute, and with 1 ml per minute it is 5.8. Analysis time is almost half, as I told. Resolution is little compromised, little less, and back pressure will be of course high with high flow rate. Now coming to column oven temperature, that is the temperature of column expressed in degree centigrade. System HPLC system with temperature 5 degree to 80 degree centigrade are available. Now why you want to adjust the temperature? So when you do experiment at fixed temperature, so you will get reproducible results. So better if you have column oven with you, you have to set particular temperature and perform the experiment. Also sometimes if you increase the column oven temperature, sometimes you will get good resolution, you will get increase in temperature will lead to fast exchange of your sample between stationary phase and mobile phase, and the retention time will decrease little bit. Back pressure will also little bit decrease, because with increase in temperature the viscosity of mobile phase will little decrease, and as there is a fast exchange of your sample between stationary phase and mobile phase, peak width will be less and peak height will be more. So sensitivity will increase with temperature. You can see from this image or from this chromatogram at 60 at 25 degrees centigrade, you can see same sample is injected, only 5 components are visible, but as you are increasing the temperature, the components are separated, well separated. Here they are hidden here. So with increase in temperature, you can increase the resolution and you will get better separation. Now coming to detection, depending upon analyte, you have to use go for detection. So if sample is having chromophore, you have to use UV detector or PDA detector. If compound is fluorescent, you have to use fluorescent detector. Fluorescence detector is sensitive than UV detector. If you are dealing with ions, you have to go for conductivity detector. If your sample is non UV absorbing or there is no fluorescence, you can go for refractive index detector. And for separation or detection of chiral compound, you have to go for chiral detector. HPLC detectors are of two types: bulk property detector and solute property detector. Bulk property detectors are used when your sample is not having any characteristic. So you have to use characteristic of mobile phase for for detection of sample. For example, refractive index detector. So if sample is non UV absorbing, non fluorescent, you have to use mobile phase refractive index for as a measure of detection of your sample. And solute property detector, it uses property of solute. For example, ability of sample to absorb UV light or ability of sample to absorb fluorescence light. So these characteristics are property of sample. So these are used when you are so bulk property are property detectors are used in such kind of samples. I will focus on UV detection. If your sample is absorbing UV light or UV radiation, you can go for UV detection. UV detectors are of two types: fixed wavelength detector and variable wavelength detector. With fixed wavelength detector, you can only work on fixed wavelength which is given by the manufacturer or kind of detector you have. And if you are going for variable wavelength detector, you can select your detection wavelength of your choice. So you have to set the detector wavelength at lambda max of your sample or absorbance maxima of your analyte. If you are dealing with two compounds, you have to use isobastic point. PDA detector, it is a type of UV detector. It will provide spectrum on in the entire range of UV visible region. PDA detector, it also gives you purity of your analyte, means you will be able to see whether your the peak which is given by analyte is due to single component or there is some impurities there or not. So peak purity can be checked by PDA detector. So what PDA detector does is, it suppose I want to check the purity of this peak. So what it does, it takes spectrum from 3 point of your peak: leading edge of the peak, peak maxima, and tailing edge of the peak, and then this overlay is produced. So if you from this diagram you can see this is impure peak, this is pure peak. So all three spectra, that is from leading edge of the peak, peak maxima, and tailing edge of the peak, they are exactly similar to each other, hence the purity match is 99.9. But here if you can see here, this red line is somewhat deviating, that means something is there, means some impurity is there, so purity match is only 76.4%. So you can say that this peak, though it is looking like a single peak, there is some impurity, means something is there here which is not resolved properly or which is not separated here, it is hidden here. So this peak is not solely due to one component, there is something hidden here. Now UV cutoff is also important aspect to be considered. What is UV cutoff? The wavelength at which the solvent absorbance is is equal to 1 in 1 centimeter path length. using water in the reference cell. So what this slide depicts different solvents which are used and UV cutoff and their UV cutoff. Um, Thumb rule is here that your sample lambda max should be greater than UV cutoff of your solvent of your mobile phase. Here you can see acetone has UV cutoff 330. So you cannot use paracetamol. You cannot go for acetone for estimation of paracetamol. You cannot use acetone as a solvent for estimation of paracetamol, because paracetamol has around 257 nanometer lambda max and acetone has UV cutoff 330. So thumb rule is there, the lambda max of your sample should be greater than the UV cutoff of your solvent which is used as a mobile phase. Also, solvents like triethylamine and trifluoroacetic acid, they degrade over time and their UV cutoff increases. So you have to keep this point into mind. Next is injection volume. Now, what is injection volume? It is a volume of sample injected in microliter. You can have manual injector, you can have auto sampler. Manual injector, where you can only inject fixed volume of sample depending upon type of loop you have selected for your HPLC. Suppose your manual injector has 20 microliter loop capacity, then you can only inject 20 microliter. Suppose you have a loop of 50 microliter, you can only inject 50 microliter. You cannot vary, you cannot change amount of sample to be injected in the manual injector. While auto sampler, you can vary your sample to be injected. It can range from 1 microliter to 1000 microliter depending upon type of loop you are having in your auto sampler. So why this parameter is important? So for that you should know what is overload, means what kind of overloading conditions are there in HPLC. You can have mass overload, you can have volume overload. What do you mean by mass overload? Too much analyte is injected, means concentration is too high of sample is or high concentrated sample is injected. And volume overload means too much volume is injected. You should not inject high concentration or high volume, because it produces tailed peaks, because the depending upon column length and internal diameter you have to inject the sample. This table depicts column with internal diameter, different internal diameter and length and volume to be injected. You can see from this chromatogram very well that when 20 microgram is injected, you can see that that is concentration overload or amount overload or mass overload. So here the two peaks are merged. But when the sample is reduced by half, that is 10 microgram, you can see well resolved peaks. There is no overlapping of peaks. Next is sample preparation. Sample should be prepared preferably in mobile phase. Means if your sample is soluble in mobile phase, you have to use that mobile phase composition for sample preparation, or that mobile phase composition as a solvent, so that you will not get any solvent peak. But if your sample is not soluble in mobile phase, at least if you go for dilution with mobile phase, then also it's fine. But if this is also not possible, it's okay if you are using different solvent or a solvent other than your mobile phase, but the solvent peak should not interfere with the analyte peak. Sonication of sample is very essential for complete dissolution of your sample in solvent. Of course, you have to filter the sample before injection, because any undissolved solid may clog the injector or it may clog the system. Some samples require pre-treatment, for example plasma and herbal extract, that is also important. Now, need for gradient evolution. Some complex samples with different polarities of components present in there, they cannot be eluted or they cannot be separated by isocritic method, in that case you have to go for gradient elution. So gradient elution is recommended for samples that cannot be easily separated by isocritic method. And in our previous slide we have seen that isocritic elution means the mobile phase composition remains constant, while gradient elution mobile phase composition changes with time. So you can see here, with different time the composition of 0.1% TFA and ACN is changing. So this is gradient programming and this is isocritic one. Now, what are the column problems that are faced during method development? Some that we will discuss. So, continuous bubble in lines. As we know that we have to purge our HPLC system so that no air bubble goes into the system or column, because it will disturb our column packing. It will produce unsteady baseline. So we don't want any bubble in our line. So if you see continuous bubble in the line, sonicate the mobile phase properly. Solution is that, and check the filters of your solvent reservoir. Next is change in retention time. If retention time is changing with same chromatographic condition, also you are getting change in retention time. So check pump performance. Use one reservoir instead of two. Sometimes it may happen that your pump is not working properly, mixing of the two components of mobile phase is not proper. So better you manually mix and prepare your mobile phase and use single reservoir, so you won't get fluctuation in retention time. Check the column. If column is not proper, or if it is very old, or the shelf life of column is over, so you have to replace the column. Very high retention time means your analysis time is very high, retention time is very high, so use strong solvent. What is strong solvent? Strong solvent is that solvent which increases the elution of your sample. So go for strong solvent. Acetonitrile is stronger than methanol, and methanol is stronger than water in case of reverse phase chromatography. You can also increase the flow rate for decreasing the retention time, or you go for shorter columns for decrease in retention time. Very low retention time, use weak solvent, because weak solvent will not cause fast elution of your sample. Or you can decrease the flow rate. Tail peak, decrease the injection volume. Sometimes it may happen that you have injected high volume of your sample, so because of that also you can get tail peak, or sometimes the concentration injected is very high. So in you either you decrease the concentration of your sample, or you decrease the injection volume. Unresolved peaks, change mobile phase and use column with smaller particle size. As we have seen that as particle size decreases, resolution increases. So with small particle you can get resolution of your peak. Air bubble in detector. So what you have to do, sometimes it may happen that air bubble may get stuck at the point of detector, and you will get continuous fashion or pattern in the baseline. So how will you remove that? You have to start the pump, and you have to close the column outlet. So what will happen, from both the ends the pressure will be created, and the bubble will be it will be broken. So you can remove that air bubble from the detector. Maintenance of column and HPLC system. Here I have listed few points for maintenance of column and HPLC system. Washing of column can be done using methanol or acetonitrile. This I have specifically written with reverse phase column. You can wash your column either with methanol or acetonitrile. Also you have to keep in mind the solubility of sample. If sample which you have analyzed is soluble in methanol, go for methanol for column washing. If it is soluble in acetonitrile, go for acetonitrile for column washing. Washing is effective at low flow rate. Very important. Washing is very effective when the flow rates are less. So you can go for 0.2 ml per minute flow rate, 0.3 ml per minute flow rate for washing purpose. In case of buffer, you have to use water. Water is a mediator between buffer and solvent. So whenever you are using buffer, before use of buffer and after use of buffer you have to give washing up to at least 1 hour with the water. Otherwise what will happen, if you directly switch over to methanol or acetonitrile, what will happen, buffer may get precipitated out. So first remove buffer with the water, then go for your desired organic solvent. Open end washing for high pressure of column. Suppose your column pressure is too high, so you can go for open end washing, where the one end of the column is opened and then washing is given. If required, you can reverse the column for proper washing of the column. Column washing duration minimum 1 hour. It's not that you have to go for 1 hour, but minimum 1 hour if you are giving the washing, then there will be effective washing, or there will be complete washing. Store the column in 80% of methane or 80% of acetonitrile. Once the work is over, now you want to remove the column from the system, you have to store into 80% of methane or 80% of acetonitrile. I am talking about reverse phase column, because if you use 100% methanol or 100% organic solvent, so what will happen, after certain period of time the organic solvent may get evaporated, so column will become dry. So 20% water you have to use, HPLC grade water, for storage of your column. Unused column should be closed with fritz, or column ends you have to use for closing of column. Reservoir filters can be cleaned using sonication in IPA or 10% nitric acid solution. Reservoir filters means the bottles into which we are placing our mobile phase, it will have filters, so that no impurity can enter the system. So if these filters are clogged, you can sonicate in IPA or 10% nitric acid. Then you can wash it with methanol, and then you can um you reuse it. Means you have to remove the filters from the reservoir. You have to take a beaker, you have to sonicate in isopropyl alcohol or 10% nitric acid. So when you sonicate it, if anything impurity is there or some clogging is there, that will be removed. And then again you have to wash the reservoir with the methanol or appropriate solvent, then wipe it properly, then you have to place into again reservoir. So this process you have to remove the filters from the system. You cannot use IPA and 10% nitric acid in the system for washing purpose of filters. Always wash the injection loop with appropriate solvent. If you are going for manual injector, or if you are going for auto sampler, so you have to wash the loop with appropriate solvent. Cleaning of flow cell is done at high flow rate using connector. If some impurities there into detector, they will show you some peaks. So if you want to remove it, remove the column, use the connector or union or coupler, and operate the system at high flow rate. So what will happen, key your impurity will be removed from the detector. Water port should be changed daily, because if you don't change it, there will be a generation of microorganism, or there will be a growth of microorganism. So you have to daily change your water port. If system is not in use, you have to remove the water port, and you have to keep the system in organic solvent. Do not keep the system or port in water when not in use. This I have already discussed. Turn on the detector at the time of injection, in the time of injection, means when you are sure that you are going to inject the sample, at that time only you should on the detector. Otherwise what will happen, unnecessary the detector will remain on, and the shelf life of detector will be reduced. So whenever you are sure that you are going to inject your sample, at that time you should uh, on the detector to save the lifespan of your detector lamp. Turn off the detector while washing the column. See, during washing, no detector is required. So what you have to do, when you are sure that your all the injections are over, all the samples are over, now you don't need a detector. So at that time you can switch off the detector, so that you can save the detector from unnecessary working. So while washing you should switch off the detector or turn off the detector. So in short, when detector work is not there, you should not keep it on. Frequently turning on and off the detector can harm the detector, but at the same time you should not turn on off the detector. And very important, whenever you are collecting the data for documentation purpose, you should use virus free device. Otherwise what will happen, if you are using pen drive or something device which has got virus, and uh, uh, you are using that virus, uh, uh, this device containing virus to your system or your computer. So what will happen, virus will enter to the computer which is attached to HPLC, and it will hamper the software performance. So this is all about practical aspects of method development. I think I have given sufficient knowledge as per my experience. So if you have any doubt, you can contact me at the given email ID. Thank you so much.